In this problem, we're looking at a system which is made up of three bodies. There's a particle over there on the left-hand side, a particle on the right-hand side, and between them is a thin, rigid bar, which we'll treat, of course, as a rigid body. We have some springs that are connecting the two particles to ground. The particles are connected to the rigid bar with these rigid links of negligible mass. And what we're going to do is describe the motion of the system in terms of the motion of the particle over here on the upper right-hand side. That is the displacement of x, where we know the springs are both unstretched when x is a 0. Our goal here is to find the equation of motion for the system. It's got three bodies, but there's only 1 degree of freedom, so we're going to need one single equation when we are done. So what I'm going to do is draw my FBDs. I've already drawn out the blocks and the bar, but I will before I move down to there. I'm going to call this block A and this block B. I'm going to call this pin joint down there O. So the forces that are acting on A is going to be the spring force over here on the right-hand side, and that spring is K times the deflection there of x. There's going to be a force that's carried by that rod there connecting A back to the bar, so we'll call that thing FA. Same kind of thing here between B and the bar. We're going to call that FB. Of course, there's some normal forces acting on A and B like this. There's a spring force over there on the left side, which I'll define more precisely here in just a bit. But here at O, there's going to be reaction forces of OX and OY. The reason I hesitate to assign a name to that spring force is what I'm going to do is define a coordinate, which I'll call Y, which describes the position for B. It's going to be positive to the right, just like X was defined positive to right there for block A. So the point there being is the spring is going to be unstretched here when Y is 0. So the force is given by K times Y. Okay, so what I've got here is the foundation for me to start out by using my Newton-Euler equations and ending up with the single differential equation of motion. I'm going to look at block A. Block A, when I sum forces in x, I get minus kx. Again, x is positive to the right. I've got an FA, which is pointing in the negative x, and that is equal to a mass times acceleration term of ma x double dot, like this. This is equation 1. I will look at block B. Block B, I'm going to sum forces in y, and that's going to be a minus ky plus fb. Note that fb is drawn to the right on B, and that's equal to mass times acceleration of block B, so that's y double dot. So there is that. Now I need to look at the bar. I'm going to write down a single Euler equation where I do a moment balance about point O. The force there of F A is going to cause a moment in the clockwise sense. So what I'm going to do as a third variable, I'm going to say that theta is the rotation of the bar positive in the clockwise sense. So what that says is that the moment due to FA, it's going to have a moment arm there of L. That's going to be in the positive theta by my definition. The FB has a moment arm of L over 2. It's going to be in the clockwise, which by my sign convention is a negative. Mass moment of inertia about O times theta double dot. So this is equation 3. And don't forget that for the homogeneous bar, the mass moment of inertia about the center of mass is 1/12 ml squared. So when I want this about O, using the parallel axis theorem, I take m times L over 2 squared, and when I add those two together, I get that IO is equal to 1/3 mL squared. So from this, I have three equations. I need to first get rid of my internal forces of reaction. So from equation 1, I'm going to write down that FA is equal to minus KX minus MX double dot. Equation 2, the force balance equation for B, that's going to be FB is equal to K times Y plus MY double dot. And so if I substitute these into equation 3, what I get is a minus KX minus MX double dot with a moment arm of L minus FB. FB is the quantity KY plus MY double dot. That's with a moment arm of L over 2. And then that's equal to 1/3 ML squared theta double dot. So we have gotten rid of these two forces of reaction of FA and FB. But we're still not done, because we need not only a single equation, but we need to have it in terms of a single variable of a motion. The question said, or asked us to do it in terms of x. So we have x. We could, if it were just an x, we would be done, but we also have y double dot and theta double dot. So we need our kinematics. The kinematics is going to help us provide that additional information that it takes to eliminate theta and y from these equations. Note that when I define my angle of rotation, I said that theta was going to be defined positive in the clockwise sense. That was just my choice. And so this variable here is x. Where b is attached, that's called y. And this angle here is the rotation angle of theta. So from the picture, you can see that x is equal to L times sine of theta. We can see that y is equal to L over 2 sine of theta. And the question says, assume that the angle theta is small. The angle of rotation of that bar is small. So this sine theta is approximately equal to the angle itself. So we can say it's approximately equal to L theta. And therefore, since this is also approximately equal to the angle of theta, this is L over 2 times theta. We need x double dot and y double dot. So we'll do x double dot is equal to L double dot theta double dot. Oops, not L double dot. L is a constant. I should have written L theta double dot. So from this, theta double dot is equal to x double dot over L. Y double dot is equal to L over 2 theta double dot. And so from this, we see that y double dot is equal to half of x double dot. So we are now in a position of substituting these back into our equation of motion. And so what we have here is minus kx minus mx double dot. We'll keep those as those. Our ky, that's going to be k times 1/2 x plus mx double dot divided by 2 times L over 2. And the right-hand side is 1/3 mL squared. Theta double dot above is x double dot divided by L. I can cancel out 1L across the board, and then this L will cancel with this. So I can combine my terms, and I get a 1/3 m from the right-hand side. If I move over the mx double dot from the first term, I add in a 1/2 m x double dot. All I'm doing is combining like terms. I have k times x. I have a k over 2 times x, and that appears to be it. So this is equal to, on the right-hand side, it's a 0. So in the end, our equation of motion for small angles of rotation, we have a 1/3 plus 3/2. So 1/3 plus 3/2 is going to be 1 plus 9 over 2. Is that correct? 1/3. Nope, that's not right. So basically, it's a 1/3 plus 3/2 mx double dot plus 3/2 k is equal, or times x, is equal to a 0. So this is our equation of motion for small theta. So as long as we restrict our motion of that bar to small angles, this is the differential equation that governs the system. What did we do? We drew a free body diagram of each body, the block A, the block B, and the rigid body. We used Newton-Euler equations on each one individually. We eliminated these internal forces of reactions of FA and FB. We did our kinematics to find the relationship between y and x, and between the angle of rotation and x, combined everything together to give us our equation of motion that's shown here.